Spot welding is a process of joining two metal sheets by applying heat and pressure at small points between them. It is widely used to model in automotive industry for strong, reliable connections. But the question is how to model this in finite element analysis to predict their behavior under load. So there are several ways to model spot weld in FEA, but for force-based method, there are two popular ways. First is the beam method, beam element method, where your beam of dia of the basically I'm assuming like the dia of the spot weld will be 6 mm, and on the basis of that I am modeling one beam, and that beam is connected via RB3 to these elements. So one is the beam element method, and second is, which is little more popular in automotive industry, is the ACM method, or we call it as hex RB3 method. Basically what you do here is you create this uh, spot welds using ACM technique. So basically, uh, this you can choose the number of nodes here where you want the spot weld, and then you can choose the component. This is it. We used to create in HyperMesh, but in any other software there will be one method. So basically, what it does is it create one hex element, and this hex element is created to RB3s, and RB3 is connected to these plates. So in this way, we used to create these spots. So basically, two popular methods are the beam RB3 method and hex RB3 method. So for calculating fatigue, we are using force-based method. There are two methods to calculate fatigue in spot weld. Basically, stress-based method, and second is force-based method. Force-based method is convenient and easy to use. So we don't want to go into much into the modeling details of nugget of this spot. That's why we are using here force-based method. So force-based method here we are going to use. So suppose these two sheets are joined by a spot, then we will request the output, nodal output, force and moment nodal output from the software, and then the FEMFAT is going to use the stresses used to calculate the stress from those force and moments of those of that spot nugget. And basically, if we are using ABAQUS or maybe Optistruct or NASTRAN, we need to request this outputs, force and moment outputs. So basically, that syntax is enforce. We need to request enforce in the case of ABAQUS, and if we are using NASTRAN or Altair Optistruct, we need to use GP force there. So suppose this is the structure I am going to analyze using FEMFAT, do calculating the spot fatigue. So basically there are two spots here, and I have created few sets here. So FE510 is this set, FE300 is this set, and the most important thing is uh, you need to do is like this is the ABAQUS deck. So ABAQUS, you need to put FEMFAT spots as the number of as these two elements, hex elements of this spot. If this is a beam, then you can put beam in that element EL set. Okay, and finally there is a fatigue set which contains this all. Okay, so once this is clear, I will export this deck, and then I will solve this in ODB, and then I can import this in FEMFAT. So in FEMFAT basic, I will read this INP. So once you will read this INP, you can see like the spot welding points will be there. So this is 4. Why it is 4? Because if you see like here, here there are two spots, okay, and these are two T spots, means uh, these are connected to two plates. So this will have 1 point here, 1 point here. So these are having basically are one spot is joining two plates and this spot is again joining two plates. So uh, this spot welding points force will be 4. Okay, and you have defined this in FEMFAT underscore spot. So if I have defined only one hex, then only 2 points will come. But in this case, I have defined both hex. So this both points will come. If this set is not there in your INP file, then the FEMFAT cannot be able to identify which are the spots. This is it. By the way, this is in ABAQUS. Okay. So now groups. So groups, I can add these groups again. Okay, which I have created, and fatigue set. Okay, this stress, I can load this stress. Okay, so once stress is loaded, you will see the number of spot elements is force data is equal to 2. Because I have requested and force here, I will show you. Requested and force here. So if you see this uh, INP file, if you read this and see this INP file, then if you see this element, star element output, element set FEMFAT underscore spot, and both I have requested enforce and enforce SO. Enforce SO is basically for beam coordinate system, and enforce is for the your global coordinate system. So it is good to request both, as enforce SO is more useful if you are designing spot welds in your FEM model using the beam element method. And enforce is useful if you are using spot hexa, um, if you are using spot weld as hexa arbitrary. Okay, so once this is clear, we will go to here again and then we can define the materials. So here there are two materials I have imported. Okay, and by the way, one more thing is like the spot properties will be same. Like the spot will always be your linear steel model. I will show you. The spot hexa will have the properties of your steel, linear steel. Okay, and this one cycle I have created as we have already know this, and then in nodal characteristic, this is the main uh, thing we will assign the materials here. So FEMPAT 300 I will do 200 and let's for here 60 microns. FEMPAT 510 I will assign as 500 and 60 microns. Then FEMPAT spot you can assign here any material, but it is necessary to assign some material to FEMPAT spot in FEMFAT basically. So I will assign this material. Then in influence factor, general factors, you can use copy this properties blindly, and I will put mean plus amplitude and favorable sequencing. And then in spot, you need to check this box to enable this spot. If you don't check this box, this spot will not be solved. So you need to check this box and then go to spot force, again check this box, sign one message you need to select, and then you need to connector diameter, you need to select it from FE geometry, and I have used the connector diameter of 6 mm. Okay, and connector material you need to select not from the connector material which we have defined is from the FEMFAT. We will as we will decide the connector material from the seat material. So how it is taken from the seat material? So basically, between these two plates, which is having the lower material properties, means weaker material properties, this pot will take that material property in FEMFAT. Okay, so again we will go to analysis parameters, and here the settings are already mentioned in my previous video, and then in here uh, in hypermesh results we can just use this DMA. So once this analysis is done, we will open this INP and DMA file in my hyperview, and then I will plot one by damage. Basically, I will reverse this contour. Let me rearrange this uh, color scale.
Okay, as you can see, like uh, you have the least damage here, and this spot is doing nothing, like it is safe. And here you have like the life is very less. And one more thing about this spot I want to showcase here is, if I go here, FEMFAT spot, let me isolate this. You can even plot this, the life of the spots. So this is how you can do the spot weld in ABAQUS. So this method of spot identification using set uh, using set will work in ABAQUS, but but for Optistruct and NASTRAN this may not work. So because the Optistruct and NASTRAN solvers uh, store their set informations in the form of numbers and property informations also in the form of numbers. Then how to do this? So basically you can simply change the property ID of your hex. uh, Basically I need to change the card image also here to something called as p solids. Okay, so basically you need to change here to 2 lakh one. So your property ID of your hex will be more than 2 lakh, between 2 lakh to 3 lakh, and for beam it should be uh, between 1 lakh to 2 lakh. So this is how you can define your spots in in NASTRAN and OptiStruct.